Download this code from codegive.com, link in the description below. Collisions in file checksums, a deep dive with examples. Checksums, also known as hash values or message digests, are widely used in computer science to verify the integrity of data, including files. They essentially provide a fingerprint of a file. If the file's content changes, even slightly, the checksum should change significantly, ideally. This allows you to detect accidental or malicious data corruption during transmission or storage. However, the question arises, can two different files have the same checksum, leading to a collision? The short answer is yes, collisions are theoretically possible and, depending on the hash algorithm and the size of the input data, practically possible as well. This tutorial delves into the reasons behind collisions, their implications, and how they relate to the algorithms used in file checksums. 1. Understanding checksum algorithms ***. Checksum algorithms work by taking an input, the file's data, and producing a fixed size output, the checksum value. Common algorithms include cyclic redundancy check, CRC, relatively fast but also relatively weak. CRCs are often used for error detection in data transmission but are not cryptographically secure for file integrity verification. Variants like 32 Costa Rican colones are common. Message digest 5, MD5 produces a 128-bit hash value. While once widely used, MD5 is now considered cryptographically broken due to the ease with which collisions can be found. Do not use MD5 for security-sensitive applications. Secure hash algorithm, SHA, a family of cryptographic hash functions developed by the National Security Agency, NSA. SHA-1, 160-bit, is also considered insecure for most applications and should be avoided. SHA-2, SHA-224, SHA-256, SHA-384, SHA-512, and SHA-3, a different algorithm family, are currently the recommended choices for cryptographic hashing. SHA-256 and SHA-512 are commonly used. Adler 32 ***, a simple checksum algorithm that is faster than 32 Costa Rican colones but provides weaker integrity protection. Generally only useful in specific use cases where speed is prioritized over robustness. 2. The pigeonhole principle and collisions ***. The fundamental reason collisions are possible is rooted in the pigeonhole principle. This principle states that if you have n items to put into m containers, with nm, then at least one container must contain more than one item. In the context of checksums, **items all possible files. The number of possible files is practically infinite, or extremely large, depending on the maximum file size you're considering. Containers the possible checksum values. The number of possible checksum values is limited by the size of the checksum, example 2 sub 128 sub 4 MD5, 2 sub 256 sub 4 SHA-256. Since the number of possible files is vastly larger than the number of possible checksums, collisions must exist. That is, there must be at least two different files that produce the same checksum. 3. The probability of collisions ***. While collisions are theoretically guaranteed, the probability of a collision for a good hash function is, hopefully, very low for a reasonable number of files. The probability depends on the size of the hash value larger hash values, example SHA-512's 512 bits, drastically reduce the probability of collision compared to smaller hash values, example MD5's 128 bits. The number of files being checked as the number of files you are comparing increases, so does the probability of a collision, even with a strong hash function. This is described by the birthday paradox, https://en.wikipedia.org/wiki/birthday_problem. The birthday paradox *. The birthday paradox demonstrates that in a set of just 23 randomly chosen people, there's a greater than 50% chance that two of them will share the same birthday. The same principle applies to hash collisions. 4. Example code, Python. Here's a Python code example demonstrating how to calculate checksums using different algorithms and illustrating the theoretical possibility of collisions, although realistically, finding a collision by accident for SHA-256 is incredibly improbable. Explanation of the code *. 1. Calculate _checksum, file name, algorithm, function *. Asterisk takes the file name and the desired hash algorithm as input. Asterisk uses the hashlib module to create a hash object, example hashlib.md5, hashlib.sha256. Asterisk opens the file in binary read mode, RB, because checksums are calculated on raw bytes. Asterisk reads the file in chunks to handle large files efficiently without loading the entire file into memory. Asterisk updates the hash object with each chunk of data. Asterisk returns the hexadecimal representation of the calculated hash value using hex digest. 2. Main function asterisk. Asterisk creates two simple text files, file1.txt and file2.txt, with slightly different content. Asterisk iterates through a list of hash algorithms, MD5, SHA-256, SHA-512. Asterisk calls calculate_checksum, to compute the checksum for each file using the current algorithm. Asterisk prints the checksum values and indicates whether a collision was detected, if the checksums are identical. Asterisk includes a section to illustrate conceptually what a collision would look like, but finding a real SHA-256 or SHA-512 collision through random file creation is virtually impossible. This section aims to clarify the meaning of a collision. Important considerations asterisk. Asterisk security implications asterisk. The possibility of collisions is a major security concern when using checksums for critical integrity verification, such as verifying software downloads or digital signatures. If an attacker can create a malicious file that has the same checksum as a legitimate file, they can substitute the malicious file without being detected. This is why algorithms like MD5 are considered broken. Asterisk choosing the right algorithm asterisk select a hash algorithm that is considered cryptographically secure. SHA-256 and SHA-512 are currently strong choices. Avoid MD5 and SHA-1. Asterisk salted hashes asterisk to further mitigate the risk of collisions, especially in password storage, techniques like salting are used. A salt is a random value added to the input before hashing. This makes it much harder for attackers to use pre-computed collision tables, rainbow tables, to crack passwords. Asterisk checksum versus cryptographic hash function asterisk. While all cryptographic hash functions are checksum algorithms, not all checksums are suitable as cryptographic hash functions. A crucial property of a cryptographic hash is collision resistance. It must be computationally infeasible to find two different inputs that produce the same output. MD5 and SHA-1 are no longer collision resistant, so they should not be used for security purposes. 5. Real-world examples of collisions asterisk asterisk. Asterisk MD5 collisions asterisk MD5 collisions have been demonstrated many times. Researchers have created two different files, example two different PDF documents, that produce the same MD5 hash value. This makes MD5 unsuitable for anything that requires strong integrity checks. Asterisk SHA-1 collisions asterisk. In 2017, a team demonstrated a practical SHA-1 collision. They created two PDF files with the same SHA-1 hash but different content. This event further solidified the recommendation to avoid SHA-1. 6. Preventing collisions, practical measures. While you cannot eliminate the possibility of collisions, you can drastically reduce the probability to negligible levels by using strong hash functions, employ SHA-256 or SHA-512. Adding salts, where appropriate use salts for password hashing. Using digital signatures. Digital signatures provide a stronger guarantee of authenticity and integrity than checksums alone. Digital signatures use asymmetric cryptography, public/private key pairs, to ensure that the data has not been tampered with and that it originates from a trusted source. Combining checksums. In extremely sensitive scenarios, you might consider using multiple hash functions, example SHA-256 and SHA-512, and comparing both values. The likelihood of a collision across multiple independent hash functions is significantly lower. However, this increases computational cost. 7. Stack overflow and collisions. On Stack Overflow, questions related to checksum collisions often arise in contexts like file integrity verification. Users may ask about how to verify that a downloaded file is the correct, uncorrupted version. Data deduplication. Checksums can be used to identify duplicate files or data blocks. Users might encounter collisions in this scenario, leading to incorrect deduplication. Password hashing. Users seek advice on how to securely store passwords, avoiding common pitfalls like using weak hash functions or not using salts. Database integrity. Checksums can be used to detect corruption in database tables. In conclusion, collisions in file checksums are a theoretical certainty due to the pigeonhole principle. However, by using strong cryptographic hash functions like SHA-256 or SHA-512 and employing appropriate security measures like salting and digital signatures, the risk of collisions can be reduced to an acceptable level for most practical applications. Understanding the factors that influence collision probability and choosing the right tools is essential for ensuring data integrity and security. Always prioritize using modern, secure hashing algorithms and avoid using deprecated or broken algorithms like MD5 and SHA-1.